training series. So this is basically the overall thing. First of all, in 11.2, we learned that in order to even have a chance of convergence, no, has to be 0. I can't believe I messed that up. Okay, it has to be 0. The limit as n goes to infinity of the terms has to be 0. Okay, so we're looking at, so in all this, we're looking at this series right here. In order for this to converge, the limits of these terms have to be 0. It has to be 0. Okay, and even if they are 0, then is not guaranteed because, for example, the harmonic series. Okay, so then that's 11.2. 11.3, the integral test. To apply this, you need all of the f of n's to be positive, okay, and increasing, and f has to be continuous and decreasing, okay? And so this is like your a-n's right here. So f of n equals, or I should say the other way around. Your a sub n's is f of n in terms of the sequence. Okay, and then that's the integral test. And then 11.4, the comparison test. Here you need all terms to be non-negative in order to apply it. And it's an versus bn. And the way that it works is if these an's are less than or equal to the bn's, and the bn converges, then the n converges. If the an's are greater than or equal to the bn's, then and the bn's in this series diverges, then this one will also diverge. Okay, so here you compare terms. So an less than or equal to bn, or an greater than or equal to bn. Okay, and this would be for all n's. Okay, it'd be either this one for all n's, or either this or this one for all n's. Okay, and then there's a limit comparison test. Okay, when we've gone over those things. Okay, alternating series, absolute conditional convergence, and then we just recently did the ratio on the root test. So we're kind of good on those. Okay, so let's get into the exercises. So number 1, test the series for convergence or divergence. Okay, so any guess on that one?
I was doing this one earlier. It diverges.
Yeah, that diverges because these terms right here. Oh, what the heck? Hold on. Okay, it diverges because the limit as n goes to infinity of e to the n over n squared is not 0. In fact, it's infinity. Okay, because this grows faster than n squared does in the end eventually. Okay, so number 2, this one right here. For this one is an integral test. If you take the integral, we can go from 8 to infinity because that goes from 8 to infinity here.
On this one, would you not want to use the root test?
The root test won't work. The root test will give you, it's going to give you L equals 1.
Oh, okay.
That's inconclusive. So the integral test is the best way to go. Also comparison, you compare, these terms are slightly smaller than the 1 over n, so, and the 1 over n diverges though, so that's kind of doesn't get you very far. And then here we have the square root of log of 6x. Oh my goodness. Okay, so this one seems to be a little bit tricky to integrate, but if you rewrite it like this, log of 6x to the negative 1/2 all over x, then the derivative of log of 6, so note that the derivative of log of 6x is equal to, okay, so it's 1 over 6x times the derivative of 6, which is 6. So it's 1 over x. So it's this part right here. Okay, so you can use, so then what you do is you just take this log of 6x and add 1 to that, so that's 1/2. Okay, now let's look at the derivative. So the derivative would be, you'd have 1/2 coming down. So let's put a 2 there to counter that. This would reduce by 1, so that gives you that term. And then the derivative of the inside is 1 over x, which is right here. Okay, and so, so basically you're looking at the limit, well, a 6 infinity minus some finite number. And so this is going to be infinity. Okay, so diverges also. Any question about that or anything?
No.
Okay, great. So let's go on to the next one. Number 3. You want to take a guess at that one?
Is this one going to converge?
Yes, this is going to converge.
Okay.
Okay, because and what you can do here is you can do comparison. Now I said that for comparison you have to have all the terms positive, and this has negative terms for some values of n. This is negative. But if you compare if you go for absolute convergence, okay, the numerator, that's always less than, this is always less than or equal to 1 in absolute value. And this is greater than 6 to the n. Okay, and then this one right here converges because it's a geometric series. And r is equal to 1/6. So the absolute value of that is less than 1. So that converges. So therefore this one, so from here, we get absolute convergence. And that implies convergence. Okay. Okay. Number 4. Let's look at number 4. This one's a little bit tricksy. But what test do you think would work out the best here?
I want to say the ratio test just because it looks like some of the examples we did with that.
Yeah, the ratio test
would work the best.
Yeah, as far as I can tell, the ratio test is the best choice by far. I can't see anything else working. But the ratio test works beautifully. Okay, so you take the limit as n goes to infinity of n plus 1 over an. Absolute value, but all these terms are positive anyways. Okay, so and the a plus 1. So you have an n plus 1 here. So that's 6 times 13 times 20, all the way up to, you'll have this term right here, but then you'll have another one. You have another term here. Okay, and then you're going to divide by all these terms. And then you have another term, 9 n plus 1 minus 1. Okay, and then this an down here is 6, 13, 20, all the way up to 7 n minus 1. And then divided by that, 8, 17, 26, all the way up to 9n minus 1. Okay, and then of course all of this cancels with all that. All that cancels with all that. And I forgot to put the limits here. It happens every once in a while. So you just get this right here. What is this? 7n plus 7. So 7n plus 6 in the numerator and 9n plus 8 in the denominator. Okay, and what happens as n goes to infinity? What's the limit?
It goes to 7/9.
Yes. And so L is 7/9, and that's less than 1, so converges by the ratio test. Okay. So number 5. Let's see here. What do you think about that one? So maybe the way to approach this would be this, okay? Think of it this way. The numerator is k and log k. Okay, the denominator has basically k cubed. Okay, and so you think, okay, one of those will cancel with one of those. So we have log k versus k squared. And log k is smaller than k. So it's smaller than any power of k. Or let's say it grows slower than any positive power of k. Okay, so log k grows slower than any positive power of k. So we could peel off, let's say, we could peel off a k to the 1/2 and then have a k to the 3/2. And that grows, that's just like, this is going to dominate this, right? And so then basically 1 over k to the 3/2, that series converges. Okay, this converges. So it's going to be convergent. Okay, but the way that you might do it is, the way that you might prove this would be comparing it with this series here, okay? So the limit, so here we'll start over again. So the limit as k goes to infinity of these terms here. No, let's not do limit. K log k over k plus 7 cubed, all over 1 over k to the 3/2. I guess we could do limit. Maybe limit is better. Yeah, let's just do limit. Okay, so here we're taking, we know that this series converges, right? This limit, dang, this one's gonna be, so that kicks the k to 3/2 to the top, right? Okay, that's k to the 5/2. Versus down here we have k plus 7 to the 3rd. Now 3 is 6/2, right? So let's write 6/2. Okay, so we know that 6/2 is more than 5/2. So you basically have k to the 6/2 versus k to the 5/2, and this dominates. And then that extra half, like I said, dominates this part. So this limit's going to be 0. I guess that's what we said right here. I'm just doing it formal. And in limit convergence, if the limit is 0 and the one in the denominator converges, okay, then in the limit 0, that means that this is smaller than that, basically in the limit. And so then it will converge. Okay. Let's go to number 6. Are there any questions on number 5?
No.
Okay. So number 6. What do you think about this one?
Alternating?
It's alternating. So,
Yeah.
and so it's alternating. And this one is like, you think of this as 1 over the square root of j. Okay, now if you have this right here, 1 over the square root of j, that's going to diverge. But because it's alternating, it will converge. So, and that goes to 0 as j goes to infinity. So this is conditionally convergent. But it means it converges, so we'll go with that answer. Okay, number 7. Now finally we have one, there's a one test that we didn't use yet, at least one test we didn't use yet, but we can use it here. The root test. Okay, so the root test. So let's apply the root test here. And so you have the limit as n goes to infinity of the nth root of the absolute values of the terms, which in this case is going to be all that. And the nth root is the same as raising it to the 1 over n. Which is going to be n squared over n. You multiply these together, multiply exponents like that. So, so then we have this right here. Right there. And this one's really, it's really hard to see what that's going to be. But I mean, you're not really, this sounds kind of weird. I mean, if you're really experienced, this is kind of weird. But if you take the reciprocal of that to the n power, so just the reciprocal of this would be this. The reciprocal of that is that. It's still raised to the n power, but it's just upside down. This is going to be, with the reciprocal, you can split it up like this into 1 plus 1 over n. Okay, do you remember what that is?
That was e to the r.
Yes, and r is 1, so it's just e. So that's e. So because of that, that's just the reciprocal. This is going to be 1 over e. Because of this. Because there's just the reciprocal. Limit of the reciprocal is just going to be 1 over, 1 over the limit. So this is 1 over e. And so what we have is L is 1 over e, and e is 2.7 something, so this is less than 1. So it converges. Any questions about that?
No.
Okay, let's go to number 8. Interesting. What do you think of number 8?
1 over n. Could you do the comparison test with this one and split it
Yeah,
into,
comparison. What do you want to compare it with?
would you end up splitting up the denominator?
Okay, okay, so here's what you do. The denominator is kind of weird. And you generally can't split denominators up, but what you can do is, get like do a comparison on it. And especially this denominator, this n times cosine squared, cosine is going to be all over the place between -1 and 1. So cosine squared will be between 0 and 1, right?
Mhm.
So this is just jumping around between 0 and 1. But this right here is this is more steady, this part right here, because it's just 1 times n, or and whatever n is. So as n gets larger, this gets smaller. What I would do here is this looks a lot like 1 over n, okay, except you have this other term right here, but this is just in the same order, but maybe smaller. But then it doesn't really matter because you have this right here. So if you, let me think. So and this diverges. So what you want to do is you want to look for something that diverges. So you want to look for greater than or equal to. And greater than or equal to means you make this denominator as large as possible, and 2n would do the trick, because cosine is always between 0 and 1. So this will always be between, will always be less than or equal to 2n, which means that 1 over this will be greater than or equal to 1 over 2n. And so these terms are greater than that, equal to that. They're all positive because this overcome. Both these terms in the denominator are positive and 1's positive. And then we know that this right here, 1 over 2n, well, that's just the same as 1/2 this. And if you take a half of infinity, you're still going to get infinity. So diverges.